All right, this is another video in the Equilibrium Part 4 series, that PowerPoint. I wanted to walk through some of what I call shortcuts and easy buttons. If you look at a really complex looking problem and you're worried you have to do the quadratic, you might not have to. So I wanted to walk through setting up a couple of those. Okay, so one of the shortcuts that I don't have on the table is if you have a very specific type of reaction where you have A plus B and the product is 2 times C, whatever that product is. What's really special about this is if you set up the K expression, you'll have something on the top that's squared. And you'll have those two reactants multiplied together on the bottom. Here's where this can get really easy. You see the square and you think quadratic. If you're given the same initial amount of your reactants, or if you're given just an amount of the product, these are going to be the same. So what happens is, let's do it this way. So minus x plus 2x on that side, 0.1 minus x, 0.1 minus x, and then 2x. Do you see how these equilibrium values are identical? So we can rewrite this 2x entire quantity squared on the top, and then on the bottom 0.1 minus x entire quantity squared. When we have a perfect square on the top and on the bottom, and this is going to be equal to some numerical value, we can just take the square root of k, the square root of 2x entire quantity squared, and the square root of that denominator. So we get whatever the square root of k is equal to 2x divided by 0.1 minus x. So take a look at that. When you can have the same thing multiplied together, whether it's on the bottom or the top, that's really a square term. And then you can just use the square root. So that's one to look out for. Another example, I'm going to go back to our problem that looked pretty crazy. Here's what it looked like. We had to find Q and the relationship to K. Oh man, and then we ended up with this hairy mess. Look, who wants to solve that? Not me, and I didn't. We stopped there because I said, you know, when you get a problem that looks like this, you're usually given something else. And a great shortcut is if you are given the equilibrium concentration of any component, any of them, because guess what? Once you have a number for one, you go back to that particular compound and you set that number equal to whatever's in that cell or whatever's in that spot on the equilibrium line for that compound. So if I'm told the equilibrium concentration of chlorine is 0.001 molar, I can set that equal to what I had set up for chlorine at equilibrium as an algebra expression. So I can set it equal to 1 minus x. Well, then it gets really easy to solve, right? You can just solve for x. You can do plus x to both sides. You can do minus 0.001 from both sides. So you get x equals 0.999. Oh, and here's where it gets really easy. All right, well now, actually, a lot of times we're not even given a number. We're asked to solve for k. So in this case, we would say, oh, now that I know what x is, I can put that value everywhere I see x. So I can say 1 minus 2 times 0.99, entire quantity squared. This one I was given, chlorine, is 0.001. 2, yes. And then on the bottom, I thought I had a little panic moment there, like, what did I didn't solve it. That's why that one looks bigger. 1 plus 2 times 0.999 entire quantity squared. Again, I'm not going to solve this one all the way out, but you would just plug it into the calculator. In this case, we would be asked for K. So ask for K. You're given 1 equilibrium concentration. You solve for X, and then you just plug it in to your expression with your equilibrium lines all written in, and that's just what you put for X in every spot. Okay, so this video is just a summary. I'm not working through an entire example. Wanted to have all of this in one place. Okay, one more that we can do is what we call an approximation. So a lot of times we will have what looks like a nasty quadratic when to ignore the minus x or minus 2x or minus 3x or whatever. Okay, so let's say we have an equation. Okay, we have initial change equilibrium. Let's say we have 5 initial for reactant A and 10 molar for B and none for C. And let's say the K is really small. It's 1.5 times 10 to the minus 30. Okay. When we are starting with reactant and have a very small K, like, I don't know, I'd say like 1 times 10 to the minus 3 or smaller, we can actually ignore the minus x. So that's minus 2x, that's minus x, and that's plus x. So 5 minus 2x, 10 minus x, and then x for C. Getting a little crooked there. When we have a very small K and we start with reactant only, remember this means reactant favored. So that means compared to X, 5 and 10, or whatever my initial amounts, are going to be very large. X is so small, this is like 0.000000000000001. So small. It's pretty much still 10. So we can ignore the minus x or minus 2x when we're starting with only reactant and the value for K is very small. So we would set this up to be K equals x divided by 5 squared times 10, right? We're ignoring the minus 2x or minus x. Here's the other example. If we have a very large K and we are starting with only products, so let's say we are starting with 2.5 and we don't have any, so this is plus 2x plus x minus x, 2.5 minus x, x and 2x. Let's say K is huge. 1 times 10 to the 25. That's a big K. Remember, a large K is product favored, which means most of the atoms at equilibrium are going to be coming together to make product. So this change is very, very small. So a large K, again, I would say over 1,000. A large K and starting with only product, it's going to stay on the product side because it's product favored. Very little is going to disassemble back to the reactant side. So we can ignore the minus x or minus 2x, whatever it is. Now we never ignore the plus 2x or the plus x. That's all that's there. So compared to 0, it's a significant amount, but compared to the amount of product you're starting with, it is an insignificant amount. And so this is what our expression would look like 2x entire quantity squared times x. All right, and that one would be pretty straightforward to solve. We're ignoring the minus x. Compared to the 2.5, it's very, very small. Okay, so this was just kind of a quick summary. The final bullet point on this slide is if you're given initial or then allowed to reach equilibrium, you're going to have to use an ice table. The only time you're not going to need to use an ice table is if you're given what you are told are equilibrium concentrations or equilibrium pressures and asked to find K. That's the only time that we're not going to use an ice table for this type of